All right, I'm going to go ahead and get things going and introduce happily our first seminar speaker, our first house seminar speaker for this spring 2022 semester. And I'm very happy that that is Dr. Darrel Kingfield. Darrel is currently working in Colorado. Before that, however, he got a bachelor's degree from in meteorology from Purdue, and then moved on to the University of Oklahoma, where we met. He got a master's in geoinformatics, which is a hybrid in cartography and geography and meteorology, and then stayed to get his PhD in geography at OU in 2017. It's at that point that we kind of met up and eventually laid the groundwork for collaborating a few years later. After graduating, he worked at SIMS, now CRO, first at the Warning Decision Training Division, and then as a research associate and scientist. Before he moved to Colorado, where he's been at Esrel in the Global Systems Lab, GSL, and is currently the Hazard Services Program Manager, which is current position. So Darrel's expertise is multifaceted and unique. He knows a lot about modernizing technology for use in watches and warnings, a lot of R2O, research to operations, idea and technology transfer, and also has a solid background in severe weather and radar remote sensing. Darrel's won several awards, including awards for his contributions to MPing. So those of you may be familiar with MPing, that an app that lets you indicate your precipitation. So researchers can use it to validate things like radar data. Also in his work in MRMS, multi-radar, multi-sensor, that's been an ongoing project down in Norman for a while. And also his work in Norman on the hazardous weather testbed, which allows researchers and operational forecasters to work together to kind of improve that relationship and improve forecasting. So Darrel and I started working a few years ago on a project of a supercell climatology, but he's not going to talk about that. Today he's going to talk about something a little different, which is ideally using, well, we've had for weather radar, our national weather radar network, we've had a number of years now where the radar scanning can be altered so that you get more low-level scans very quickly, which ideally is used when there's severe weather to get better information close to the ground. And so what Darrel wanted to know was, what are the pros and cons of that? And using this increased low-level scanning, is it actually, can we validate that it's actually providing forecasters better data and improving their warning skill? And so with that, Darrel, please take it over, and thanks for being here.
Yeah, thank you very much for the introduction. So yeah, this is a project that I've been working on, tinkering with for about 6 years with Dr. French, and its conclusions will be published in an upcoming issue of Weather and Forecasting. It's currently an early online release. And as Michael mentioned, what we're doing here is we're examining effectively a decade of decisions on how we choose to scan the atmosphere and its effects on National Weather Service warning decision-making, and how we observe thunderstorm hazards using radar. So the United States has one of the most comprehensive Doppler weather radar networks in the world. That was built throughout the 1990s and today consists of about 159 S-band Doppler radars covering the continental United States and select locations abroad. One of the key benefits of using S-band radars is that these frequencies are not easily attenuated. So we can see long distances from the radar dish, making them optimal for scanning severe weather phenomena. During the initial rollout of the WSR-88D, the benefits for identifying hazardous weather were immediately recognized. In an initial study by Polgar and co-authors in 1994, sites with the WSR-88D were 5 times more likely to issue a tornado warning for a storm that ultimately would go on to produce a tornado. And there was a 20% decrease in the number of unwarned tornado events. And this support was further solidified by a National Academies of Sciences report that showed that the WSR-88D is a major component of the entire atmosphere observing system and is the primary means for detecting, tracking, and nowcasting thunderstorms and their attendant hazards. So today, the National Weather Service forecasters that come in have to take about 40 hours of specialized training on radar data collection and interpretation as part of their onboarding process. So the point that I'm driving home here is that the WSR-88D network is at the forefront of our observational ability to detect and track thunderstorms and their hazards. So let's dive a bit deeper into how the radar collects data. So every radar scans in a 360-degree circle at various elevation angles relative to the radar horizon. A collection of these elevation angles together is called a volume of data, and the strategy that describes what angles are scanned is called a volume coverage pattern, or VCP. So in the example that you see here on the right, we are showing VCP number 12. This volume consists of 14 elevation angles that span from 0.5 degrees to 19.5 degrees above the radar horizon, and they're scanning vertically in order. This is how we've been doing VCP scanning for quite some time now. So different VCPs do have different strengths and weaknesses that forecasters can choose from, really depending on the kind of information they want to receive from an ongoing precipitation event. So for example, VCP 12 provides more dense sampling of lower levels of the atmosphere, while VCP 11 provides more dense sampling at higher levels of the atmosphere. And there is VCP 21, which generally provides fewer elevation angles, but those scans themselves actually have much higher data quality. So in addition to these VCPs, there's also 212, 211, and 221, which scan at the same elevation angles as 12, 11, and 21, but perform their velocity range folding and corrections differently. This is an algorithm that's called SZ2 and is recommended for use really when dealing with tornadic, damaging wind, or events that require velocity interpretation, particularly further from the radar. At its peak, there were around 7 non-surveillance VCPs that were available for forecasters to choose, but this number has been declining in recent years, particularly with the addition of VCP 215 in 2018, which really replaced the need to have VCPs 11, 21, 211, and 221. So in addition to VCPs being changed as we develop new techniques, algorithms, and strategies, natural disasters that effectively cause catastrophic damage can also spur improvements. So for example, after the EF5 tornado struck Joplin, Missouri on May 22nd, 2011, it was revealed that this storm had a very rapid low-level intensification, and most of it occurred between the 2 lowest elevation angle scans, which at the time, there was about a 5-minute gap between those scans. So we had one scan of the storm, the tornado formed very quickly, and by the second scan, it was almost too late. And so from the service assessment report that came from this event, it was recommended that more volume coverage pattern sub-strategies be implemented to rescan the lowest level of the atmosphere more frequently. This led to the creation of 3 supplemental scanning strategies shown here on the screen, and these could be attached to any of the existing VCPs. So there's supplemental adaptive low-level scanning, or SAILS, which was implemented starting in 2014, and this adds 1 extra low-level scan in the middle of the volume. This was followed by multiple elevation option SAILS, or mesosales, in 2015, which adds 2 or 3 low-level scans, extra low-level scans throughout the volume, followed by mid-volume rescan of low-level elevations, or MERL, which can rescan the lowest 4 elevation angles from 0.5 through 1.8 degrees above the radar horizon a second time. So in each of the animated figures on the slide, you can see that radar beam dropping back down to scan the lowest 0.5 degree angle or the lowest 4 angles more than once before reaching 19.5 degrees above the radar horizon, which does signal the end of a radar volume. So these strategies really kind of broke the mold of, we're not just scanning from the lowest to the top, we're actually jumping around now throughout the collection of a single volume. So as a result, there are pros and cons to these strategies. The pros is that, there is a greatly improved monitoring capability of the lowest elevation angle when sails is activated. It produces around 71% more updates at that lowest level per hour. But unfortunately, scanning that lowest elevation angle, which is 0.5 degrees above the radar horizon for most sites, is the most time-consuming angle to collect. And that results in an increase in the revisit time for subsequent angles that are scanning mid to upper levels of the atmosphere. So anything beyond 0.5 degrees in the case of sails or mesosails, or 2.4 degrees above the radar horizon for Merle will effectively could be delayed between 4.5 minutes to up to 6.5 minutes between successive scans. So right before these sales strategies were implemented, there was another large modernization made to the radar hardware, and that was to support dual polarization capabilities. Now, this allows for a horizontal pulse and a new vertical pulse to be transmitted and received by the radar. Now, the inclusion of a vertical pulse allows for the scrutinization of the vertical dimension of targets, which really gives us a better idea of the size, the shape, the orientation, and the variety of hydrometeors and targets that are being measured by the radar beam. Now, this also allowed for new base products to become available for the forecasters to interpret, and that includes differential reflectivity, or ZDR, which is the ratio of horizontally polarized reflectivity to vertically polarized reflectivity, and is proportional effectively to the aspect ratio of hydrometeors that are small relative to the radar wavelength. Now, in an interpretation example on the right, the addition of a ZDR field can give us a lot more information about information inside this single convective cell. So the region with moderate reflectivity at horizontal polarization and these a little bit warmer colors, so small to moderate ZDR, indicates that there could be small to medium drops in this region of the storm. Looking to its right, where we see higher, more warmer reflectivities here with even larger ZDRs that are much greater than 0, that indicates that this area could be experiencing larger raindrops in the storm. And finally, we have very high reflectivity, as we see it by the purple here, exceeding 60 dBz, co-located with around near 0 ZDR, really boosts confidence that hail could be falling in this region, because a ZDR near 0 signals that these targets below the melting layer are spherical in nature and cannot be small because reflectivity is so high. So, just by adding this secondary field, we can start discriminating and breaking out different hydrometeor types within a single storm. So dual polarization radar itself has been a game changer for scientists to scrutinize the microphysical characteristics of precipitating systems. And since its rollout, there have been many new signatures observed and documented. So for example, the ZDR column, which is defined as a region where raindrops are being lofted above the environmental freezing level, resulting in a positive ZDR being measured in a region where ZDR values tend to be more muted. This signature alone has been documented to being a proxy for updraft location. It can assist with hail nowcasting, be an identifying characteristic as to whether a thunderstorm could turn severe or not, and as recently has been shown to serve as a predictor for peak tornado intensity. So in the figure on the right here, you can see this warm area that's above the 0 sea level. That indicates a ZDR column with this storm right here. So researchers and National Weather Service forecasters have received some very big advancements into how we collect information from the atmosphere and the type of information that's collected, but they've all been kind of accordion together. Many sites received their dual polarization upgrade and then the ability to turn on sails with only about a 12 to 18-month gap. So it's possible that much of the data that's been collected since the dawn of the polarimetric era could be having fewer scans at mid to upper levels of the storm, but there's many unknowns as to what is that impact, if there is one, and how extreme it is. So this really led to many questions that we wish to address in the study. So the first is, there's a lot of VCPs available, up to 7 non-surveillance VCPs at one point, and we wanted to see, well, what was the breakdown of those VCPs used during severe thunderstorm and tornado warning operations, as well as during these thunderstorm reports, which is tornado, hail, and thunderstorm wind reports. From that, we then wanted to see when sails became, active and at the various weather radar sites, how often was sails being used at those warning decision-making moments, as well as near storms that were producing reported tornadoes, damaging hail, and thunderstorm winds. And from that, if sails and mesosails and Merle was being used, and was available at a warning decision-making point, did that actually boost or improve warning performance? But on that front as well, we wanted to evaluate a secondary variable to see, well, maybe, sales was being turned on for another region. And so we wanted to see if there was a relationship between the potential for widespread organized thunderstorms and then the usage of sales, which we analyzed through the collection of Storm Prediction Center watches. And finally, we wanted to determine how long a single volume of radar data is taking to scan and how that value has evolved over the past decade to determine, are we actually seeing certain mid to upper level features less now than we have been before? So to answer all of these questions, we had to start collecting a lot of data. So first, Weather Service warnings. So this warning data set came from the National Weather Service Performance Management webpage, and we parsed over 200,000 warnings to get the warning location, area, start time, and whether or not that warning was verified by a storm report. Now, we used the warning tracking location, which is the actual physical cursor location that the forecaster drags the dot to determine the closest WSR-88D that was to that trackable object. And then we used its issue time to get the window of radar data that we needed to examine. The thunderstorm hazard data set also came from the National Weather Service Performance Management webpage, and we downloaded all tornado reports, hail reports with a hail size greater than 1 inch, and thunderstorm wind reports with a magnitude greater than or equal to 50 knots necessary to verify a warning. We used the report location to determine the closest radar, and the report time to determine the window of radar data to download. So it is known that the storm data database isn't perfect, and there are possibly errors in the report time and location, et cetera. However, given that in this study we analyzed over 250,000 storm reports, we have to assume that a vast majority of these are correct. And if the storm report was grossly wrong and in an area, it was likely being scanned by a surveillance volume coverage pattern and would have been excluded from the analysis anyway. So we just have to keep that in mind. So with every warning and report having its closest radar known and the time window necessary, the next step was to download an even larger amount of radar data. This ended up being about 20 terabytes. We used the NexRad on AWS to download a bulk of the level 2 NexRad files. And then we've gap filled that information with volumes that we got from the National Centers for Environmental Information, or NCEI, because for some reason, not all the data exists on NexRad on AWS. And maybe that's the case now, but it wasn't definitely when we were working with the data. So just a warning on that. So each warning or report had about plus or minus 30 minutes of radar volume data downloaded from it. And we used the Python ARM radar toolkit, or PyArt, to determine the VCP number and whether or not sales was running. And to do that, we just looked at the order of the elevation angles in that volume. So a volume with 1, 2, or 3 extra low-level scans was defined as sales 1, sales 2, or sales 3. And a volume with an extra scan at the lowest 2, 3, or 4 elevation angles was classified as MERL 2, MERL 3, or MERL 4. So overall, about 96% of warnings and reports did have radar data on one of these archive systems meeting the time requirements, and they were included in the analysis. I will note that we also analyzed a data subset, which corresponds to, warnings that were unique within 30 minutes of each other. So we actually removed duplicate warnings or warnings that were in close succession or reports that were in close succession within 30 minutes to really examine if there was any skew in the data that could be introduced by, maybe outbreaks or events with a high number of reports. And the sample sizes of the subset are actually also shown in the table on the right. They will not be reported on, particularly in this presentation, but the general result is that the trends were effectively the same between the subset and the full climatology. So let's start answering all of these questions. So the first is, what VCPs are NWS forecasters using in their warning decision-making process and were found near storm reports? So focusing first on NWS warnings, we do see that forecasters did opt for using VCP 12 or 212, which again provides that dense low-level scanning coverage at the lowest levels of the atmosphere. Even with upwards of 7 VCPs to choose from, about 86% of warnings in any given year had we're running VCP 12 or 212 right at that warning decision-making point. Now, for tornado warnings, there were a greater ratio of warnings using VCP 212, and this is expected given the benefits of the enhanced velocity de-aliasing with that SC2 algorithm. Other volume coverage patterns really accounted for a dwindling amount of warnings over time, with fewer than 5% being used for either severe thunderstorm or tornado warnings. So really, VCP 12, 212, and then with the introduction of VCP 215 in 2018, as shown in the purple on this graphic, really highlight a vast majority of the VCPs that were used. So it was a pretty good call to retire a lot of those other VCPs. They really weren't being used. Thunderstorm reports also find us and follow a similar pattern to severe thunderstorm and tornado warnings. There are about 89% of reports having its closest radar in either VCP 12 or 212 within a given year. And since the beginning of the polarimetric era, so this is us going back to 2011, VCP 12, 212 accounts for about 95% of all storm reports. And then with the introduction of VCP 215, that's about 2% of the reports overall. So 3 VCPs, each with the same set of elevation angles below 10 degrees above the radar horizon, were used near 97% of all storm reports. And that's good to know because that shows that there's a bit of a climatological consistency on how the lowest levels of the atmosphere are really being scanned over the last decade. And the overall share of reports with a nearby radar running in VCP 12 and 212 increased when looking at significant severe reports, which includes tornadoes rated EF2 or stronger, hail sizes greater than or equal to 2 inches, and wind reports greater than or equal to 65 knots. Now, this was also notable to look at because significant reports and storms that produce significant reports are really more likely to be used for case studies and other scientific analyses of why certain thunderstorms are producing these dangerous hazards. So there are 3 main VCPs that are being used nearby most warnings issued and storm reports that have been logged in the database. And which is good news because these 3 VCPs are also where you have the greatest number of sales options for selection. So VCP 12, 212, and 215 will be the 3 VCPs that will actually focus our attention on for a bulk of the remainder of the study to really determine how often these sales strategies are being used near warnings and reports. So looking first at the usage of sales and mesosales in warning operations, we find that sales strategies were really quickly adopted during their initial rollout in 2014, with over 71% of severe thunderstorm and 91% of tornado warnings using some sort of supplemental strategy in any given year since 2015. Sales 1, which produces 2 total low-level scans per volume, was more widely used in severe thunderstorm warnings, while Sales 3, which produces 4 total low-level scans, was more commonly used during tornado warning operations. So overall, since about 2011, around 40% of severe thunderstorm warnings and 25% of tornado warnings were issued with no sales strategy running. And most of these warnings actually occurred prior to 2014, when sales wasn't even available. So really, over 90% of tornado warnings, and in this case, over 75% of severe thunderstorm warnings in any given year now are being run with sales. So we expect that as the years go on, there's going to be an ever shrinking data set of storms that were scanned without a sales strategy. Moving over to storm reports, we do find that hazard type follows a similar trend to warnings that are verified by that hazard type. So tornado events, which are likely to verify tornado warnings, are more likely to be running a sales strategy with a higher number of low-level scans. As you can see, Sales 3, which is indicated here in red, accounts for a majority of these reports, particularly since its first full year of implementation in 2016. Hail and wind reports, which verify severe thunderstorm warnings, were really more likely to have a sales strategy running than not, but adopt one that had fewer extra low-level scans. Sales 1 was the more dominant strategy overall. There was only 1 year with thunderstorm wind reports where it tied with Sales 2, but in all other years, Sales 1 by and far was the most common sales strategy that was selected. So since the dawn of the polarimetric era, going back to 2011, 3 out of every 4 tornadoes that have been reported have been actually scanned with some form of sales strategy running, and around 60% of hail and wind reports have had some sort of sales strategy running. So already a majority of thunderstorm hazards scanned in the polarimetric era are having more low-level scans and fewer upper-level scans. So when examining significant severe reports, we do find that slightly fewer tornado reports and more hail and wind reports had its closest radar scanning with some sort of supplemental strategy. And we postulate that this is because convective environments that are conducive to tornadogenesis are really also producing these significant severe hazards. So you'll get baseball-sized hail with a tornadic thunderstorm. So with that information known, we know that now a majority of warning decision-making moments and storm reports, that closest radar was running with some sort of sales, mesosales, or MERL strategy. And this led us to the next question, which is whether or not this information being available at the closest radar to a warning decision-making point resulted in those warnings being more likely to be verified by a storm report or providing the forecaster more confidence to produce that warning. But first, we need to get into more methods, which is how we collected this information. So for this analysis, we computed two different performance metrics. The probability of detection, which is the percentage of hazards that were inside an appropriate warning, and the false alarm ratio, or FAR, which is the percentage of warnings that did not have an appropriate hazard inside of it. So what is an appropriate hazard for a warning? Well, a hail report with 1 inch or greater diameter and a wind report that is 50 knots or greater will verify a severe thunderstorm warning, and only a tornado report will verify a tornado warning. But we have to consider the case of a hail or a wind report that actually falls inside a tornado warning, because in reality today, if a wind or hail report does fall within a tornado warning, it will be counted as being within a warning, which would boost that hazard type's probability of detection, but the warning itself wouldn't verify, which would boost that warning's false alarm ratio. And so in this study, we actually excluded these kinds of reports from our analysis because we did not want to effectively artificially inflate the probability of detection for hail and wind reports, and rather focus on whether the forecaster issued the appropriate warning for the hazard expected. We did perform some significance testing at this level by first building a distribution of data using a non-parametric ordinary bootstrap, and then taking that and using a non-parametric one-sided Mann-Whitney U-test to evaluate whether more low-level scans did correspond to improved performance. So here we have the receiver operating characteristic plot that shows both severe thunderstorm warning performance as annotated in these circles and tornado warning performance as annotated in the triangles. We find that severe thunderstorm warnings overall had a higher POD and a lower FAR than tornado warnings. They are more situated towards the upper right of the plot, which is better. And that both severe thunderstorm warnings and tornado warnings that had its nearest radar running with 2 or 3 extra low-level scans or MERL did have a higher POD and a lower FAR than the national averages. These are denoted by the filled in black circle and the black triangle here as well. Furthermore, when we compare warnings that were issued with no sales strategy running from 2015 to 2020, when other sales strategies did exist, and compared its performance to 2011 to 2014, when really no other sales strategies existed, both severe thunderstorm and tornado warnings saw a statistically significant decline in overall performance. Now, we attribute this to a lower overall use of a VCP without sales in recent years, because as we've seen, more often than not, people will be using a sales strategy in warning or near storm reports. And back in 2011 to 2014, because there were no sales strategies around, we're just seeing the general average across the board. So outbreak events or events that are highly conditional, were also being included here, which, were more likely to be highly verified. So zooming in on the tornado warning portion of this plot does show that enhanced separation, particularly for sales 3 in terms of POD and FAR, really compared to other sales types. Sales 3 tornado warnings did have a statistically significantly better performance than all of its other scanning counterparts here. And a similar behavior was observed between sales 2, which is this purple triangle, and sales 1 and no sales as well. So tornado warnings year over year tended to have a higher POD and a lower FAR with sales 3 or sales 2, really compared to sales 1 or no sales. And so, yeah, those were the core metrics that we saw, both in a yearly analysis and in a bulk sense, as described on the slide. Focusing in on severe thunderstorm warnings of the plot, we do see that sales 2, sales 3, and MERL all had a similar POD with about 84% of wind and hail hazards near radar in that scanning mode being verified by a warning. MERL itself, which is this yellow circle here, was really only used for a small fraction of all cases analyzed and did have the lowest false alarm ratio of these sales strategies. But we postulate that this is because National Weather Service training does recommend the usage of a MERL strategy, particularly during quasi-linear convective system modes, which can produce severe hail in its developmental stages and more widespread severe winds during its mature stages as well. But in general, both Sales 2 and Sales 3 were statistically significantly better than Sales 1 and no sales, but not statistically significantly better than each other. So given this information, it may actually be better to use Sales 2 for scenarios where severe thunderstorm warnings are going to be the most prevalent warning mode to really speed up that volume scan collection time by around 30 seconds. So given that we know what events are verified by what warning, we took this information and calculated the hazards that had a positive lead time by supplemental scanning strategy. So here we define positive lead time as a hazard occurring at least 1 minute after warning issuance time. So looking from no sales to Sales 3, we do see particularly a large improvement in terms of the detection of tornadoes with positive lead time, with around 35% of tornadoes with a radar scanning no sales versus 74% of tornadoes with Sales 3 running having this positive lead time trend. There's a positive trend that's also seen for wind and hail reports, but there is more of a plateau that's seen, particularly for hail reports between Sales 2 and Sales 3. There's only around a 1% increase of hazards with a lead time at this stage, and it further supports the previous claim that really there's minimal value added between Sales 2 and Sales 3 in convective regimes where hail and wind are the anticipated hazards. So we're seeing that in general, warnings with a nearby radar running Sales 2 or Sales 3 tend to have a better performance than its associated hazards and have a better lead time than Sales 1 or when no sales strategy is being used. But this led to the question of, was there another factor that could be triggering the planned usage of a sales strategy, such as the forecasted potential for organized thunderstorms? And so for this, more data, more methods, we chose to look at the severe thunderstorm and tornado watches that were issued by the Storm Prediction Center in Norman, Oklahoma. All watches from 2011 to 2020 are available on the SPC website, and we use the universal geographic codes and timing information from the product text to determine what warnings and hazards were inside each warning type or outside of a watch to get area altogether. And so we did find that we analyzed about over 3,700 severe thunderstorm watches and over 1,700 tornado watches. And folding this data set into our analysis reveals several things. First, we did find that 61% of severe thunderstorm warnings and 35% of tornado warnings did occur outside of any SPC watch altogether. Of about 21,000 severe thunderstorm warnings issued since 2016 with no sales strategy running, 75% of these warnings were issued outside of an SPC watch box. And of the 721 tornado warnings issued since 2016, 48% of those warnings were issued outside of an SPC watch box. Now, these percentages do decline to about 43 and 32% of cases respectively, which when examining radars running with 4 extra low-level scans. So, mesosales, the highest mesosales that you can have. So effectively, with an SPC watch out, offices that have warning responsibilities inside that watch box were more likely to have a supplemental low-level scanning strategy running. For tornado watches, it was Sales 3 for both severe thunderstorm and tornado warnings. And for severe thunderstorm watches, it was Sales 1 for severe thunderstorm warnings and Sales 2 for tornado warnings, respectively. Breaking down whether or not a severe thunderstorm warning was verified by an appropriate hazard by watch type does reveal that cases running Sales 2 had the highest verification percentage both inside and outside of an SPC watch box. Warnings with Sales 2 or Sales 3 running nearby had a greater verification percentage than Sales 1 or no sales outside of an SPC watch box, which is shown here on the column on the left. So given these results on top of the trends seen in the performance and lead time analyses, it again shows that there doesn't seem to be any substantial benefits to using Sales 3 over Sales 2, particularly when near storm environmental conditions are conducive to producing hail and wind hazards. Performing the same analyses for tornado warnings does reveal that a higher percentage of warnings with a nearby radar running sails 3 compared to warnings running sails 2, sails 1, or no sails did verify. When no SPC watch was out, about 33% of warnings issued with a radar running sails 3 verified, compared to about 20% of warnings issued with a radar not running sails at all. So, 1 out of 3 warnings verified with sails 3, 1 out of 5 warnings verified with no sails running. So this ultimately leads us to our final question, which is where we examine how the mean radar update times have changed over the last decade with all of these new strategies in place, and how does that really translate to examining some upper level atmospheric feature. So in order to quantify how the adoption of sail strategies can really cause a slowdown in detecting these mid to upper level features, we decided to pick our lovely ZDR column to determine which elevation angle it would be seen at every storm report and location. So in this study and other studies, the location of the ZDR column has been defined as being detected around 1 kilometer above the 0 degrees Celsius isothermal level. So for every storm report in the study, we grab the closest 1-hour rapid update cycle or rapid refresh analysis grid, calculated the 1 kilometer height above the freezing level, and then use that to determine the closest radar elevation angle that intersects that height level. So of the 189,206 potential ZDR column locations that we did analyze, around 99.3% of these locations were found above the lowest elevation angle. And this includes all ZDR columns that were detected within 50 kilometers of a WSR-88D site. So this means that effectively the selection of any sail strategy will increase the time between these higher scans from 31 to 93 seconds for VCP 12, 38 to 114 seconds for VCP 212, and around 53 seconds for VCP 215. And examining volume scan times for the most complete volume near a tornado report over the first decade of the dual polarization radar era, we do see a notable increase in volume scan completion time as more sails options do become available. So from 2011 to 2013, which can be seen in this left plot, around 16% of radar volumes collected near tornadoes were actually collected faster than a standard volume of data would take to be collected. So how is that possible? Well, there was another software platform that was installed at the radar sites that's called Automated Volume Scan Evaluation and Termination, or AVSENT, which would terminate a volume early. So a volume wouldn't scan all the way up to 19.5 if it found minimal radar returns discovered at 2 successive elevation angles, at least 6 degrees above the radar horizon. And so that allows for effectively certain hazards to fall on the left side of this plot here. But by 2015, which was the first full year of Sales 1, as shown in the orange on this plot here, around 60% of tornadoes were taking, of radar volumes that were scanning tornadoes were taking about 15% longer to be collected. And moving over to the right plot, which is 2016 through 2020, we find that over 30% of volumes were taking 45% or longer to complete. And so we can see all the way out on the right here that actually about 35% of volumes, yeah, right here, this right here shows about 45% delay over what would be a standard volume time. So for hail and wind reports that are not shown particularly in this presentation, these delays are not as bad, but still over 69% of hail and wind reports had its closest radar volume completing slower than normal in recent years. And 40% of those volumes were taking over 30% longer to complete. The reason why we don't anticipate that this is as dramatic is because, again, for wind and hail reports, we're seeing less usage of Sales 3 and more usage of Sales 1 and Sales 2. So you are getting a slightly faster volume. And so from 2014 to 2020, the median volume scan time for a tornado near VCP 212, which is the most commonly used VCP, as we have shown, went from about 297 seconds to 368 seconds. So over a minute longer today. For hail and wind reports, the median volume is taking around 39 seconds longer to collect. So over a span of an hour, these delays are resulting in at least 2 fewer scans per hour. But when you adopt a more aggressive sales strategy or even Merle strategy, this could mean up to 4 fewer scans per hour. So this ultimately can have adverse effects on really any radar feature that you're trying to track above 0.5 degrees above 0.5 degrees for sales and beyond 2.4 degrees when you have Merle ×4 running. So a lot of questions have been asked and a lot of topics have been covered. So let's give a highlight of all of the statements that we have found. So in the first decade of the dual polarimetric or the dual pol radar era, we did find over 93% of severe thunderstorm warnings, 96% of tornado warnings, and 95% of storm reports were scanned with a VCP providing more dense low-level coverage. That's that VCP 12 and 212. And with sales, mesosales, and Merle coming online starting in 2014, these strategies, these sub-strategies were rapidly adopted and really activated nearby a majority of warnings and storm reports, particularly in recent years. Sales 3, which does provide those 4 total low-level scans per volume, is the most commonly used strategy near tornado warnings. And Sales 1, which provides 2 total low-level scans, is more commonly used in the support of severe thunderstorm warning making decisions and its associated hazards. From a performance perspective, warnings with Sales 2 or Sales 3 did have a higher probability of detection and lower false alarm ratio, and a greater probability of hazards in these warnings also had a positive lead time compared to Sales 1 or no sales. In several analyses, particularly of severe thunderstorm hazards, there was a negligible difference between Sales 2 and Sales 3 when it really comes to severe thunderstorm warnings and the nowcasting of wind and hail hazards. So again, maybe a good idea to use Sales 2 and Sales 3 for more convective setups where hail and wind are the predominant threat, because we want to speed up those volume scan collection times, mainly, even if it's by 30 seconds or so. And while the data suggests that we should be continuing to use sales strategies during severe weather operations, particularly for tornado warnings as shown here, there may be other factors that were not analyzed in the study that could be contributing to forecasters making more confident and accurate warning decisions. In this particular study, we did examine warnings inside and outside of SPC watches and did find that sales strategies were more likely to be activated in environments where you had the enhanced potential for severe weather hazards. But however, we did also find that outside of severe thunderstorm watches, warnings that were supported by a Sales 2 or a Sales 3 observation were more likely to be verified than warnings issued with no sales. But unfortunately, we've now determined from the study that the rapid adoption of sales is resulting in increased times between successive scans, particularly at or above 0.9 degrees above the radar horizon. And given that the NWS's mission to protect lives and property, I don't really see these scanning strategies going away. But as a result, we at least need to start acknowledging that we are not seeing features at mid to upper levels of the atmosphere as frequently as we were before, even in the early stages of the polarimetric era. And this is especially the case for many popular signatures that we're seeing throughout the literature, like the ZDR column, which would be adversely affected by this in over 99% of cases analyzed just in the study. So as a result, just because the radar didn't see it does not mean that it did not happen. And that definitely could be the case as we continue to do analyses with information from more recent years. So with that, I will end there and leave this slide up and take any questions.
Okay, thanks, Darrel. Great talk. If anybody has any questions, you can raise your hand or just talk or chat. Any of those are fine. I guess I can start. Working on this project, I think an open question is really because it's the newest strategy and hasn't been around for very long, and so forecasters aren't used to it, is what's going to happen with Merle? Do you expect use of Merle to increase, and compared to sales 1, 2, or 3, and how you think that usage might evolve over the coming 10 years, let's say?
Yeah, Merle was really built for a very specific case, which was the QLCS, because they really wanted people to diagnose quick tornado spin-ups, which may not happen at the 0.5 degree elevation angle. And so we have seen generally limited use of that so far. Merle isn't really attached to VCP 12 or 212 like it is with VCP 215, because I think they also want that enhanced data quality to be able to see maybe a more transient rotational signature that you see kind of on the forward flank of the QLCS, that you need VCP 215 to kind of diagnose that. So I just think it hasn't given the same opportunities as SAILS and mesosales has been used. And yeah, I mean, we have had at least 3 full years with it right now, and yeah, it's not even breaking in. It's not even breaking through like the other ones did. I mean, when SAILS 2 and SAILS 3 as part of the mesosales package came online, and the adoption just skyrocketed, and I think it was just because of the VCPs it was attached to. So, you know, I think it does provide some value, but I mean, the volume scan times, particularly above 2.4 degrees, really are atrocious from an analysis standpoint. I mean, we're talking over 7 minutes between successive scans, and it's causing some trouble, as we have seen in our studies when we've been looking at columns and mid-level features.
Okay. Other questions for Darrel? I was also, something else that obviously the study doesn't take into account is, just there's a ton of data here. I think it would be interesting in the future to get some forecaster feedback on this. What would they say, for example, if you were to argue, well, really, if it doesn't look like tornadoes are very likely and it's more like a severe weather, hail or winds, tamped down from using SAILS 3, maybe they had some type of retort to that and says, well, no, actually we're doing it because of some other reason that we're not taking into account. Do you think this information can be used to start a good dialogue with forecasters and maybe get some of their feedback that we haven't taken into account so far?
I think so. Yeah, I think that's a good point. And in addition, I mean, potentially what could be driving an office using SAILS 3 is, maybe the media market in the region uses their data to put graphics up on TV. And so they're saying, well, we want to see as many low level scans as possible, even if it's not advantageous for the convective setup in the situation. So that could be a factor as well. But then anecdotally, we're also seeing that sometimes people just change the VCP because of a shift change. And like just someone else comes on shift and then they're the lead meteorologist and they just say, we're going to use VCP 12. And we'll see, like at the key shift change marks, VCPs will be changing across the country as well. So it's kind of like, I feel like that there are a lot of complicated factors there that would need to be addressed, but at least throwing this out there and saying, we've had 10 years of data and kind of this petri dish where people have just been doing what they want to do, and these trends are emerging. And now, yeah, we should have the dialogue which says, hey, this is what this means, and this is what it's resulting into. And I think a bigger element here is a lot of this radar data is folding into our numerical weather prediction capabilities. And I want to see how, even getting, vertical wind profiles, radar-derived vertical wind profiles is adversely affecting maybe the initialization of the RAP, the HER, and, kind of use that as an angle too, because maybe then if we can get better short-term numerical forecasts by using lower SAILS options, or at least governing that, then we could show that it may be advantageous to find a common ground to just say, don't always use SAILS 3 or don't always use MERL 4 if it's not warranted. But yeah, this I think is the first, just kind of throwing it out there to spur all these questions so we can have those dialogues.
Any questions for Darrel? Okay, yes. Go ahead, Alyssa.
Yeah, hi, this was an interesting talk. My question is, I guess, I've never been a forecaster, so I can't kind of comment on this too much. Maybe you have more insight since you've kind of worked with them. Do you think having this many options of these like low scanning techniques is maybe a bad thing? Like there's too much choice and maybe it should be, the number of choices should be reduced for the, I don't know, the best ones?
I mean, I think that would frankly be a good idea. I mean, it's so easy to put one of these things in. I mean, they're like, oh, well, just after 6 degrees, just drop down. And then after 8 degrees, just do this. So like putting in the pattern is pretty straightforward to do. And I think, you know, I think really in an initial state, this was just like, well, it's going to produce you're going to get a low level look at the storm every 89 seconds instead of every 265 seconds. So like, why wouldn't you do this? But, you know, big picture is we were directly addressing the recommendation from the surface assessment, and yeah, we just weren't thinking big picture on some of these other things. I mean, yeah, at this point, I think it's a good conversation to have, to say, you know, if these aren't needed, then why, or if they're not being used or they're not showing any value, and these other ones may be more advantageous, then yeah, maybe we should deactivate those. But I mean, like that's a conversation with so many tri-agency organizations. I would have to do that, and it's very hard with anything that kind of goes out into the Weather Service, as I can personally attest to, is once you put something out there, it's very hard to take it away, because there's going to be one person that is like, you know, that like sits in their office in Duluth and they're like, I use it and I continue to use it. And it's like, no one, like, that was part of the WSR 57 even before the WSR-88D came out, and they're like, we need storm structure. And then we're stuck with this product for decades that, you know, is out there. And I feel like the same thing is going to happen with sales. There'll be someone who's like, I love Sales 1, or, you know, Sales 2 is the best. Don't ever take that away. And so yeah, it's a fine line, because it was like the service assessment came out. It's like, we need to do something here. This has to get out. It is advantageous, as we're seeing, that sales is providing a marked improvement, but for the greater scientific community and potentially the numerical weather prediction community, this loss of information may be hindering how we develop new conceptual models for thunderstorms, how we even maybe forecast or do provide elements for upper level observations, which have, you know, widespread aviation impacts. So, you know, tuning that knob backwards could be advantageous, but it's so hard, you know. And then the National Weather Service Union could get involved, saying that we're doing it, that this could be an unfair work burden on the forecasters. And so a lot of politics and a lot of entities really get involved when we try to take stuff away as a result. So the best way to go forward at this point would be the development of best practices training. And I believe that at least this initial study and parallel studies that we know are being done could provide the baseline information to then, you know, we then train the forecasters, say, we know that you have all these options, but try to use like these three, and then go from there. I think that's going to be the best way forward.
Yeah, no, that makes sense, and I can see why it's a really tough problem, and why it would be, yeah, tough to take some away after they've already been out there. Thank you. This is really interesting.
Yeah, I would say in general, you know, we know that forecaster overload is becoming a thing with too much info. And so, related to what Alyssa asked, do you think this is it? I mean, do you think there's going to be other options that are going to be added, or do you think they've kind of covered enough ground here where, you know, we're not going to get to a place where it's just you know, 5 additional low level? You think we've reached the end here?
I don't think so. I think there's always more room to go, and I think we're seeing it right now. I think it's VCP 112. I need to go back. But a VCP was actually just introduced last year that's actually doing back-to-back Doppler cuts of the lowest level. So, and I guess this is supposed to be used mainly for hurricanes. So now you'll get a 0.5 reflectivity, a 0.5 velocity, and then another 0.5 velocity. So you'll get like 2 velocities back to back, which is then like, I imagine volumes in the future will be like 0.5, 0.5, 0.5, 0.5, 0.5, 0.9, 1.3, 1.8, and like they'll start just doing successives, and then you'll be getting literally 20 or 30 second updates. And you know, I worked with some prototype phased array radar technologies back in 2015, and we brought in forecasters to diagnose very, you know, low probability events. Such as, you know, EF0 tornadoes that are very hard to diagnose and issue a warning with positive lead time on. And when we gave them 1 minute information from the phased array radar, they actually did perform and produce more confident warning decisions better. And you know, while we're nowhere near the ability to do phased array radar across the country, it shows that doing kind of what VCP 112 is trying to do right now with back-to-backs, that we can end up with more back-to-backs going forward and just eliminate those observations. So I don't think there's no bottom to where we can go with supplemental scans at this point.
Chris, you have a question, go ahead.
Yeah, hey Darrel, great talk. sort of going off of what you just said, that back-to-back scanning is, other than just more rapid low-level scans, are they doing anything like different PRFs to try to do better velocity unfolding? Is there any purpose to it other than just faster refresh times?
That's a good question. I'm not sure if in that particular case, if maybe they're doing like a low frequency and then a high frequency PRF back to back. I would have to read more, particularly in that case. But I do know that exists. And right at the tail end of our data set, we did start noticing some of our cases were starting to be used with that VCP as well. So yeah, that would be good for me to look back into. And I think it'll be really interesting, particularly as we diagnose, circulations, particularly in tropical systems going forward, because that's, I mean, nothing's going to beat mobile radar, things that can provide volumes, 40 seconds a minute, especially, or atmospheric imaging radars, which are really good. And I think they're really trying to create something that's like that with our S-band network, or at least try to. But, we just need to find a good common median. But this is the scientific space that we're playing in right now, and there's strengths and weaknesses to everything.
Well, so I guess that goes back to, I based on what you're saying, then if you think it's just going to keep moving forward, I think what you said at the end when you were answering Alyssa's question is very important, and that's best practices. How important it is to work with forecasters and get their feedback. And it'd be nice to know if they're overwhelmed. Maybe they're not. I mean, maybe it's, we know they're overwhelmed in other areas, but maybe this isn't one of them.
Right.
And providing them this type of data so they have better information about what to choose is probably the best way to deal with it.
Yeah.
Okay, any other questions for Darrel? Well, this was really great. Thanks everyone for coming. Thank you, Darrel, for a terrific talk. If you ever want to talk to Darrel about anything, you can shoot him an email. Well, it's just darrel.kingfield@noaa.gov, right?
Yep.
Okay. And he'd love to talk to you about it. Otherwise, thanks everyone for coming today. Thank you, Darrel. And we will see you next Wednesday for our next seminar. All right. Have a good day, everyone.